So, this talk I just thought would be interesting, basically because it's almost we are almost on the eve of 100 years of general theory of relativity, because on November 25th, 1915, Einstein wrote his paper, which was basically called the field equations of gravitation. And in that particular year, in that he almost wrote 4 papers, and this was the last paper. Please sit down. Yeah, I won't eat you. You can sit in the front. Can you see the view graphs clearly from that side? Otherwise, come in the middle. Okay, so let me repeat again what I said before the set of people arrived here. So, this talk is basically motivated because 1915, November 25th, Einstein wrote the paper which is called the field equation of gravitation, and therefore, next year this would be the centenary of general theory of relativity. Now, therefore, it is a good time for you to understand what is this theory all about? Why is it that we should understand what this theory is, and why is it not just something of interest only to physicists, but to all of us? It should be part of our culture, and that is why I thought that at your stage, at this particular stage, when you are entering into physics, you should understand this glorious heritage which belongs to our particular subject. Now, as you know, when you learn physics, of course, general theory of relativity is supposed to be a very complicated theory, supposed to be very mathematical, and people feel that it was one of the most complex theories. At some particular point, it was believed that only 4 people in the whole world understood this particular theory. Now, what I will try to tell you is that to really understand this theory today, it is not very complicated. There are some technical parts which of course are complicated, but there are the physical parts which you would be able to understand. And as you would have realized when you learn physics, physics always builds on what was done in the past. So, whenever we have a new theory, we never say that the old theory is wrong. We always say that the old theory has been extended. The old theory had applications in a limited regime, and this new theory surpasses it, because otherwise we will never make progress. Suppose every time you make a new theory, the old thing has been thrown away, then all the successes of the old theory will be lost. Remember, Newton's theory of gravity is more than 300 years old. When Newton gave his theory of gravity, after that many successes happened. We understand how the moon moves around the earth, how the planets move, how the comets move. So, if Einstein's theory of gravity replaces Newton's theory and does not match Newton's theory, then it is losing all the successes of Newton's theory. So, this is something which you will always find, that better theories of physics extend the realm of validity of the older theories. Okay. So, I will not say Newton is wrong, I would just say Newton's theory of gravity applies to a certain regime, and Einstein's theory of gravity is a better theory, and it applies to even larger realms of parameter space, and that is why it is a better theory of gravity. So, as I said, therefore, I have made connection with Newton, but then Newton also did not come from the open sky. Newton came on experiments which were done earlier by Galileo. So, if you ask me today, modern physics or modern science in some sense as we know it today, where do we really put our finger on? I would say it is Galileo. And therefore, it is good to begin our story of something very, very modern like Einstein's theory, trying to make connection with what Galileo said. And why did I say Galileo in some sense is the father of science? Basically because Galileo was the first person who emphasized that we can understand things about nature only by doing observations, only by doing experiments. You can't close yourself in a room, just start thinking and come about our understanding of the world. Our understanding of the world can only come from really doing observing nature and trying to do sensitive experiments so that we can isolate what really is at play, and only by this experimental method we can really understand the nature. Okay? So, that is the reason it is a good idea to start this particular talk with going back to Galileo. So, what I will do now is basically go back quite a few parts. In fact, the way I have structured my talk is that the talk is really made up of 4 parts, and I will try to pause between each of these parts. We can have a small discussion on that particular part, digest it. If there are not too many difficult questions which I cannot answer, then I will go ahead so that we can reach the 4th part, because the 4th part is when we learn what Einstein really did. So, let us begin with the part 1. So, this is Galileo, and the most famous book which he wrote is something which is called the Dialogues Concerning Two New Sciences. Again, for those of you who want to be practitioners of science, it is very important to read the original sources. For example, it is very difficult to read because it is written in a slightly different style and so on, but it is only by reading these original texts you really understand how a person thinks. And therefore, if you have the time, try to get your hand on this particular book. It may be available in some libraries and so on, and try to read it. Now, what is the main message which I want to convey to Galileo? I have already said that he basically believed that you should do experiments, and by these experiments he concluded that if you want to have laws of nature and you want to have them in the simplest form, then if you try to understand motion, then there is something which people were believing based on what Aristotle said, which was wrong, completely wrong. Aristotle believed that if you push a body, then it will just come to rest. Whereas he said that, well, that is what you are observing, but that is not the simple thing, because it is really stopping because of something very complex which is happening, something complex which is related to the friction between these two surfaces. So, if I can think of an idealized situation where I can do away with friction and then move a body, then I will find that the simple law of nature is that if you leave objects to themselves, they will keep on moving with uniform velocity rather than come to rest. So, again you can see that hundreds of years before him, Aristotle has come up with something. Aristotle said this and people just believed it. Galileo said, well, you can do this particular experiment, and this is exactly what he did. He set up inclined planes, tried to make it as smooth as possible, and tried to say that you should do experiments and then extrapolate them to what you can imagine is the simplest case, and that is what he did. But then when you look at this particular sentence, it says it will keep moving with uniform velocity, and he said that the simple law of nature. But then the question you can ask is, 2 questions which immediately come up. When you say something is moving, you have to answer, you have to tell me it is moving relative to what. And the other question which you have to answer is, when you say simply, it is simply with respect to which observer. So, you can see that by very hard work, Galileo has come up with a very profound insight. But the moment you come up with a profound insight, it raises 2 more fundamental questions which you have to answer. And this you find will be the nature of science. Science comes to a conclusion, but if it is a good conclusion, it has to raise new questions, which again if you answer, your level of understanding will become better. So you can see that when you talked about Galileo, immediately two questions came up. Now these questions of course were answered by Newton, and this is what led to his notion of what I will explain as absolute space and the notion of inertial observers. You will see that whatever I am telling you is actually textbook physics. You have learned this in your school when you first started learning physics. You have learned Newton's law of motion, you have learned inertial observers, but you have never realized that there is something very profound about these particular statements. It is not just a bunch of statements which you learn to pass an exam or solve a problem. It is something which gives us insight about how nature or how the world around us is constructed, and that is what is the message you should take away from this particular interaction today. So Newton answered it. He said the motion is relative to something which we call absolute space. So when you say the motion is simple, it is simple with respect to what? It is simple with respect to an imaginary space which you construct, which we call absolute space. And this is something which his famous book, which is called the Principia, in that he tried to explain what he meant by absolute space. He said absolute space in its own nature, without relation to anything external, remains always similar and immovable. That means absolute space does not change because you move. There is a notion of absolute space which is by itself, and whether I am at rest relative to that or whether I am moving with respect to that, that space really remains by itself. It is not very different, and that is why he uses the word absolute. And then the other question is, what are the observers with respect to whom the laws are simple? He said that the simple description of motion is with respect to a class of observers which we call inertial observers. And what are these inertial observers? These are observers for whom the first law of motion is actually true. So when you learn the laws of motion, sometimes you always wonder, the second law of motion says F equal to ma. So if I put F equal to 0, A is equal to 0. So why should I have the first law independent of the second law? You can always imagine that the first law is just a special case of the second law. The reason why Newton talked about it as an independent law is basically because it gives you the definition of what is meant by an inertial observer. It is only an observer for whom the first law is true, that will be an inertial observer, and it is for him that the law of nature will be simple. If you go to an observer who is accelerated, if you are not talking about an observer who is moving with uniform motion, but you sit in a merry-go-round, then you know that the second law of motion is not applicable. The second law of motion becomes applicable only if you introduce what you call pseudo forces or inertial forces. So the law of nature is not very simple if you take accelerated observers. It is only simple if you consider inertial observers. So you can see that after Galileo, Newton has come about. We are just studying mechanics, but by talking about, when you are studying the laws of mechanics, you are saying something about the space in which we are all living, right? So, and how does this thing come? It is really coming from the experiments which you are sort of doing. So the experiments which we are doing is really telling us something about the space in which we live. Let us take it ahead. So you learn the laws of motion in your class, and what kind of things do you learn? The first thing you learn is that mass is a measure of inertia. If I have a very heavy body and I apply the same force, it will move with smaller acceleration. If it is a smaller mass, so how much inert a body is measured by this property which we call mass. Then you learn about the three laws of motion, and this is what we call Newtonian mechanics. And then we go back to something which Galileo himself had realized, and he said, which he had said, that when you write down the laws of mechanics, they are the same for all inertial frames. That means if I am in a frame which is steady or at rest, and then you sit in a train which is moving uniformly with respect to me, both of us will discover the same laws of Newtonian mechanics. The law of mechanics, the second law of motion for example, will not be different for you and for me. This is what is called the principle of Galilean relativity, that the laws of classical mechanics are the same. Now, immediately after that you also learn, for example, when you do your simple course in mechanics, that if two observers are moving at constant velocity, you can write the transformation between them, and this is what you call Galilean transformation, that one frame is moving relative to another frame. So, if you measure the x coordinate will change by the amount by which it is moving. And then we also will say that the time measured in one frame and the time measured in the other frame is really the same. Now, you realize that from this simple law you derive what is called as the velocity addition formula, because you just differentiate the velocity. If you differentiate with respect to time, then you know that the velocity is changed, velocity in one frame is related to the velocity of the other frame by the velocity of the frame itself, right. If I throw a ball, if you measure the velocity of ball from a moving train, the velocity of the train has to be added to that. So, that is exactly what is called as the velocity addition formula. But when you derive it, you are using this particular formula, that time in one frame and time in the other frame is really the same. So, not only you are assuming space is absolute, you are also assuming time is absolute. And again Newton realized this, and in Principia he says time is an absolute, and in that he says absolute true and mathematical time of itself and from its own nature flows equably, that means uniformly, without relation to anything external. So, irrespective of whether you are at rest or whether you are in an aeroplane which is moving at 1000 kilometers per hour, the time which you measure according to Newton really will be the same. Your clocks have to run at the same rate. So, this is something which underlies Newton's mechanics, the notion of absolute space and the notion of absolute time. And how are we, where are we getting to this particular idea? As I said, we are really doing experiments, we are really comparing mechanics in one frame and another frame, and from that we are coming to this particular conclusion. So, if you ask mathematically how you represent it, we actually do measurements, and therefore we know if I want to measure or describe the position of a particle here, I have to give 3 coordinates. I have to say how much it is above the floor, and on the floor what is its x coordinate and what is its y coordinate. So, again by observations we have found that space is actually 3 dimensional. What about time? Is time 3 dimensional? No, we just require one value, one number to represent time. So, mathematically we will say time is just 1 dimensional. So, buried in all this elementary physics which you have learned in your intermediate in your 12th standard is the idea of what space and time consists of if you believe Newton. Okay? So, that is exactly what it is. So, we know that space is 3 dimensional, time is 1 dimensional, and according to Newton both are absolute concepts. That means they do not depend on the state of motion of the observer. That means even if you are moving in a spaceship which moves at, let us say, 10,000 kilometers per hour, the laws of mechanics will be the same or should be the same as if you were at rest. And you can say that is an amazing thing, and it is not without consequences. It is precisely because of that when you sit in an aeroplane and you pour water, you do not have to do something very complicated. You just have to do as you pour water on the earth, that is exactly what you do, even though you are moving in a plane which is moving at 1000 kilometers per hour, right. So, that is the important point about the principle of relativity, that the laws of mechanics are the same, and therefore you do not have to do anything different if the frame is moving at uniform velocity. But suppose the aeroplane jerks and stops. If you are pouring water, what would happen? A spill. So, obviously it means that your whatever you are doing, that effect of acceleration had to be taken into account. The laws are no longer the same, right. We will come to that, how this simple statement transforms into something else.
So, you don't see any contradictions to those statements you have been alone. Are there any contradictions to those statements?
That is the story, part 4. Okay. So, then Newton, so as I talked about, I talked about Newton, he talked about his laws of motion, But there was another profound thing which Newton talked about and discovered, and that is the law of gravitation. And what is this? This is basically Newton discovered what you learn as the inverse square law of gravitation. So, the important point is that anything which has mass will create a force which is called the gravitational force. So, if you have two bodies of mass m1 and m2, then there is what we call as the universal inverse square law of gravitation. The force between them falls off as 1 by r square. It is proportional to the mass of this body, it is proportional to the mass of this particular body. There is a constant which we call Newton's constant, which we call g, and that is a statement of nature. How do you discover g? You cannot imagine what g is, you can't find it out unless you do experiments, and that is exactly what you do. You really try to measure the force between two particles and then try to say what this g is. Now, look at this word inverse, you understand, inverse square means you understand, universal. So, what does universal mean? It means it has to be there for everything. Anything which has mass has to have gravity, you can't escape from gravity. Okay. So, what was the important philosophical implication of it? The philosophical implication of it is the laws of an apple falling on the earth, or the moon moving around the earth, or the earth moving around the sun. The force of gravity which occurs between them is really the same. Anywhere in the universe, if two particles have mass, they will have to obey this law. So, particles, during Newton's time they used to say you have things on the earth and whatever was outside was called the heavens. So, people always believed up till that particular time that the laws of bodies in the heavens and the laws of bodies on the earth, they cannot be the same, because we are material things and they are heavenly things. This immediately tells you there is no such distinction. There is the laws of nature, and anywhere in the universe that law of nature should be the same. So, you can see how these simple things which are just coming from simple experiments are really extending our understanding of what the universe is made up of. So, this is Newton's law of gravitation. I just want to take you one step ahead from Newton's law of gravitation, because you have learnt about this. We know that there are tides on the earth. Now, how do you understand the tides? For example, suppose I have the moon and if I have the earth, if there was no inverse square law, if the force of gravity was the same, then the force of gravity on this side and the force of gravity on this side will be the same. So, on this particular body at the center, the force here and here will sort of cancel. But we know that the force is not constant, it is a 1 by r square force. So, the force, because this is closer, the force will be larger, the force here will be smaller. So, if I take away from this force whatever is the average force at the center, on this earth, on this particular side, because there is more force, the force will act in this direction. On this side, because it is a smaller force, if I do this minus this, the force will obviously act in this direction, and similarly if you do vector calculus, you will get this. So, because of the fact that the gravitational force falls off as 1 by r square, if you have a finite body, it is not the force itself, but the derivative of the force which is effective, and the derivative of that particular force is what causes the tidal force. And therefore, if you have a body like the earth, it will be sort of pulled in one direction and squashed in the other direction, and therefore, if there is a water body on this, of course, it will cause tides. And you can see that. So, there were many things which Newtonian gravity helped us understand: the motion of the moon, motion of the comets, motion of all the planets, etc., etc. And therefore, if you come up with a new theory of gravity which loses all this, then it is, you are losing 300 years worth of work. So, obviously, you will never do that. So, always keep in mind that this is the paradigm by which physics proceeds. Just 1 minute. That whenever you come up with a new theory of gravity, in some sense, when you go to the limit of the Newtonian case, then all these things should be recovered. So, the theory will have all the successes of the old and new successes because it applies to other things. Yeah, go on.
I don't understand how the force acting is acting towards that direction, because none of the forces are facing that way. So there is a
No, remember what I explained, what I am doing here. Here I am drawing the force at each of the points. Here what I am doing is I am taking away. Now, once I know the forces, I want to know on this full body, because of the moon, what is the force which is acting. So what I decide is, I say, okay, at the center of this particular body there is a certain amount of force. So I go to another system of coordinates where I take away from all these vectors this much force, the force which acts at the center. So here the arrow is bigger, this arrow is smaller. So when I subtract the force will act in this particular direction. When I take this particular point, this arrow is larger, this arrow is smaller. So the force will act in this particular direction. But as far as this particular, so what is sort of shown here is the force acting on this particular surface. See, I am taking away this particular force, right. So this one, so this number is there. So if I just subtract out the force acting on this particular point here, right, then on this particular point the effective force will be what? On this particular surface. See, now I think the force is in this particular direction. Now I am taking away from each of these particular bodies a vector corresponding to this, right. So on this particular surface there will be a force which will be pushing in this particular direction. See, here this force is sort of smaller than, see, the force is sort of falling away, right, from here to here to here, the force is sort of falling away. Now what is the net, suppose I want to find out on this particular surface what is the net force acting. See, because the behavior of this particular body will depend on what is the net, what will be the force which will be acting on this particular body. So if I am just thinking of the force acting on this particular thing, what I will have to ask is that if I looked at this particular body, okay, how do I sort of say it? See, what is being told is that this fluid body, because of the presence of this, because of unequal gravitational forces acting on this, if this were a material body, then the force acting on this would have this configuration. That is what is sort of being told here. Another way of, if you want to sort of mathematically think about it, you basically say that, I have this particular body acting on this, and then you ask what is the derivative or what is the gradient of this particular force which is acting on this particular body. Now when you do that, you will find that that particular force will have this configuration, that it has a nature of pushing something in one direction and squeezing it in the other direction. Think about it. So as I said, this way of explaining, saying that just take away the average force, is just a kind of a loose way of saying this particular thing. That is, think of the forces acting on the body and try to ask if I can subtract away in some sense the force acting at the on an average, then on this particular body what will be the forces which will be sort of remaining. Okay. So loosely this is what you are doing, but exactly when you sort of need to do it, as I said, you have to really take the derivative of this particular thing, and then the force turns out to have this particular configuration. But it is a good question. The way I explained it, I don't think it is good enough. So you can think about it. It's a good way of saying how do you see this, more simply than what I have tried to say. Okay, so this basically finishes the old story. As I said, between the part 1 and the part 2, I just want to sort of pause. So we will get to we'll take questions on the first part, and then we will go to the second part. Yeah, please sit down. Don't stand up. Yeah.
I understood what mass is actually. That means according to Newton, it is some kind of like quantity of matter, things like that.
Yeah.
But I saw the statement when we come to quantum mechanics that we find that there is a
We,
probability.
yeah.
There is a probability of finding the.
No. Just let's cut it. We are not talking quantum mechanics at this particular point. So we don't know. So the one important point you have to understand is we are talking classical physics, classical gravity. So no quantum questions today. Yeah, the quantum questions can come at the end.
We find that S electron has a probability of finding.
That's what I'm saying.
At the nucleus.
It's a different thing, right? I'm talking about a body which is classical. So for them, the S state is the same thing as what we describe classically. So don't bring that particular thing. I think you're just confusing the issue.
As I think classically,
No.
one person cannot stand in place of the other person. It's,
Correct. But that is. I'm just saying that don't confuse the issue. If you want to ask that question, which is not based, in part 1, I didn't talk about H cross or anything like that. So you can't ask that question. I'm just telling you the rules by which this interaction session is going to be happening. If you want to talk about quantum mechanics, come to a session where we discuss quantum mechanics. No, please don't ask that question. I don't want, that question is not entertained here, because then it defeats the purpose of the interaction session as we visualize it. So if you want to ask this question about quantum mechanics, ask it another session or towards the end of the thing when general questions, if we have time, we will come to it.
Even that I haven't understood what mass is. Practically, we can understand it as quantity of matter.
That is exactly what it is, because we are talking about the situation. We are talking about the situation as it was in 1600, and mass is supposed to be intrinsic property.
If everything is vacuum, how can we understand mass?
But what is vacuum? And I didn't. What is vacuum?
If electron can stand in place of nucleus, it's some kind of saying that it is.
No,
something
as I
like
said.
vacuum. So practically, I can't stand in place of.
No.
others.
So I think it's fine. I think you're. No, you are confusing. I don't want you to confuse the class. So please, keep your questions on what we are sort of discussing. So on what I have asked, if you have a question, you ask me. But or you can link it to what I have said, I will answer it. But if you are talking about vacuum and quantum mechanics, come to a lecture where we talk about quantum mechanics. I'm not going to answer it today. No, please. As I said, since you broke the rules, I'm not going to entertain questions by you. You follow the rules.
Sir, about what he said.
Yeah.
So the thing is, he said that he didn't understand why the forces were in opposite directions.
Right.
That would,
Yeah.
All the forces are facing that direction, so the resultant can't be this.
Yeah. So one way to understand is, let's say these are the two. They are in essence. This is greater than this is greater than this.
Right.
And see, this B is the resultant of all the forces at every point. So to find the tidal force here, what you do is you subtract C minus B.
Right.
Now you can imagine this is smaller. So C minus B will be negative. It will be in the opposite direction as C.
Exactly. I think that's exactly that's exactly what I was trying to say. Yeah.
Vectorically, it is written the opposite.
Yeah. There is an issue of sign there. Yeah. So as I said, I'm going to be strict with you, because the most important thing is to be disciplined about what you're going to do, and just throwing words is not going to help, because I have met you in another session where you ask questions which you think are very profound, but unless you really have your basis right, you can just ask nonsensical questions and believe that you're talking profound things. I don't want to encourage that. So as I said, if you want to discuss, if you think you have something profound to say, please meet me outside the class or in my office, and then we can talk about it. But I don't want you to interrupt the flow of this particular class, because I really think that the purpose of this interaction is something else, and not to answer your fundamental difficulties about how the world is constructed. Okay, before we go to the next part, as I said, is there any specific question on what we have discussed up till now? Because we should not come back to this particular thing. So if we have no questions, then we move on to the second part of the story. And the second part of the story begins with Einstein, 1905. Those of you who remember, in 2005 was the year of physics, where it was celebrated as the year of physics, basically because in 1905 Einstein, in his fantastic year, in that particular year, produced 3 outstanding papers which essentially gave us 3 different branches of physics as we know it today. And one of them is what I am going to refer to, that is the special theory of relativity. So, we began with the principle of relativity as given by Galileo, where I basically said that Galileo had basically mentioned that the laws of mechanics are the same in all inertial frames. But then Einstein said that, well, I have something more general. I believe that the laws of physics, not just mechanics, are the same in all inertial frames. In a sense, what he did was what one can say, he completed Galilean relativity, and he asserted that physical processes, not just mechanical processes, are independent of the uniformly moving reference frame in which they take place. What it really means is that in trying to understand physics, we may find it convenient to break physics into mechanics, optics, solid state physics and so on. But when you really analyze a particular experiment, in that particular experiment all possible things are happening at the same time. If there is a law of nature, that law of nature cannot apply only to mechanical phenomena and not apply to some other phenomena. It is a very artificial thing, because that division of mechanics, optics and so on is something which humans have created. It does not exist in nature. We create it because for convenience we try to simplify so that we understand a complex thing in terms of smaller, simpler things. So, it does not make sense that we have a principle which applies only to laws of mechanics. So, Einstein basically felt that if you cannot tell me whether you are at rest or at uniform motion by a mechanical experiment, you should not be able to tell me whether you are at rest or at uniform motion in a frame, even if you do an experiment in electromagnetism or you did an experiment in optics and so on. So, that was his basic point, that either the principle of relativity should apply to all laws of physics or it should not apply at all. Then another point. So, this is something, it was just his understanding of how a law of physics should be. But that is not the full story. The important part of the story is this statement, that the speed of light in vacuum is the same for all inertial observers. Again, this is something which you come about, but it is not something which you can believe only by theoretical considerations. Only by doing a lot of sensitive experiments, analyzing all the experiments which you have done till then, you could come up with such a conclusion, and this is exactly what he finally said. He said that, well, people have tried to look for the speed of light in different frames, but all experiments somehow seem to indicate that the speed does not depend on the frame of the inertial observer. The speed of light is really the same, and that is what the experiments really show. So, the important point is that in some sense it is violating your common sense, because I told you that as soon as you believe Newtonian mechanics, we have velocity addition law, and according to velocity addition law, if you have the speed of light in vacuum in one frame as being c, if I am moving relative to that, the velocity should be c plus v, c minus v, or something like that. So, obviously it violates the common sense velocity addition law, and therefore, obviously I had told you that velocity addition law, in that is implicit the notion of Newton's absolute space and absolute time. So, if you start questioning this velocity addition law when you bring in the speed of light, in some sense you are directly questioning what the notion of space and time which Newton had. And therefore, when you learn your special theory of relativity in your class, you do various things, and then you learn that the notion of simultaneity and hence of time and hence of space, they really become observer dependent or relative. That means the notion of time t prime equal to t is no longer true, because when you look at the transformation between the two frames, when you make this assumption, it is not Galilean transformation, but Lorentz transformation, and therefore, the time measured in one frame and the time measured in a frame moving uniformly with respect to that time is really different. So, an experimental fact like this immediately throws away our notion of space and time as being absolute quantities. And this is basically Einstein's quote about the nature of time. He was trying to really understand how to understand electromagnetism and special relativity consistently. And again, like all his struggles, he basically said that after 7 years of reflection in vain, the solution came to me suddenly with the thought that our concepts and laws of space and time can claim validity insofar as they stand in relation to our experiences, and that experience could very well lead to the alteration of these concepts and laws. By a revision of the concept of simultaneity into a more malleable form, I thus arrived at the special theory of relativity. So, basically, if you do not give up that time is absolute, you cannot understand the experimental fact that the velocity of light is the same in all initial frames. So, if nature tells you that the velocity of light is the same in all initial frames, then this theoretical assumption which Newton made about absolute space and absolute time has to be modified because of experience or because of experiments. And it is only by giving up the absolute nature of space and time can you understand the experiments related to the constancy of the velocity of light. And this is exactly what he says, that once you accept that, then you understand the special theory of relativity. So, what we learn is that special relativity compels us to re-examine the notion of absolute space and time, and it alters them and makes them relative notions, because space depends, your time depends on your state of motion, space depends on your state of motion. So, they are all not absolute notions, but relative notions. And what is unified, the only thing which you can think of which is better than that is this notion which you call space time. So, what you really visualize is that what is it that we are doing when we do physics? What we do is we basically look at various events which are happening, and we try to say, what is the relationship between these events. Now, to understand these events, what do you need? You need to say where it happens and when it happens, and that description can be given by any observer. So, if you have an observer at rest, you can say when it happens, where it happens, that will be your description of the event. Another observer will give it another space coordinate, another time coordinate, but that event is really the same. So, that event is the same, that event is labeled by one observer as xt and another observer as x prime and t prime, but the collection of all those events is the same, and that is what is called as space time. So, the moment you believe in Einstein's special theory of relativity, the nice object in terms of which we can think of physics is this notion of space and time together. It is just a collection of all events which happen in the past, future, now, etc. That is what is called space time, and depending on your state of motion, you will have some notion of space and some notion of time, and another observer will have his own notion of space and another notion of time, but both of you are observing the same event. So, the important point is, so the last other point which will also sort of came up from special relativity is that the speed of light turns out to be a limiting speed for all interactions and particles in nature, and nothing physical can move faster than the speed of light. So, the way you understand it is by saying that, well, Newtonian mechanics needs to be changed, the notion of inertia needs to be changed, because not only rest mass has inertia, even kinetic energy has mass, and therefore, if I start trying to apply a force on a particular body, because its energy keeps increasing, in some sense its mass is increasing, and therefore, finally I find out from my laws that I cannot really approach the speed of light. If it is moving with a speed less than the speed of light, it will always move with speed less than that of light. If it is moving at the speed of light, it will always move at the speed of light and never less. So this is something which follows from the transformations which relate to observers, that is the Lorentz transformations. So you can see that starting from something which was absolute, Newton's special theory of relativity in 1905 brought us to a different picture of space-time. And where did it come from? It came from an experimental fact that many experiments proved that the speed of light is the same in all initial frames. It is not something which just comes from pure speculation, it comes from an experimental fact. So that essentially finishes the second part of my story, which is a 2-slide summary of what special relativity, what is the revolution which special relativity brought about. So before we go to the third part, on this second part, just this part related to special relativity, are there any questions? Yeah. Yeah, so what he basically meant is simultaneity is no longer absolute. Simultaneity can be dependent on the state of observation, state of motion of the observer. So he is giving up the notion of time being absolute and making it more flexible, saying that time can be relative and therefore the notion of simultaneity can be relative. And because he is giving up that notion of time, he can understand that the speed of light can be the frame in all initial frames and make a consistent transformation between a frame at rest and a frame moving at uniform velocity. Yes, yeah.
So the last sentence that
Yeah.
Nothing physical can move faster than light.
Yeah.
So is it the conclusion of the special relativity?
Yeah.
Is it the like final conclusion?
Okay. In science, there is never anything final, right? So this is the important thing you should keep in mind. I mean, unlike religious leaders who know the absolute truth, right, and nothing can be beyond that. In science, we know that tomorrow we will be corrected. So looking at all the experiments which we have done up till now, and our understanding of those experiments and our interpretation of those experiments, we feel that this particular conclusion. So for example, you must, if you read some popular book, you would have heard about the notion of tachyons. These are supposed to be particles moving faster than the speed of light. So when you look more critically at the Lorentz transformation, it turns out that what really special relativity implies is you cannot change the character of the particle. In the sense, if it is moving with speed less than the speed of light, it will always move, you go to any frame you like, it will always move with the speed less than that of light. You cannot make it move at the speed of light. If you are moving at the speed of light, if a particle is moving at the speed of light, you cannot make it move slower, or you can't make it move faster. If you are moving at a speed faster than that of light, you can never make it move at the speed of light or less than the speed of light. So there are these 3 separate categories of particles. Experimentally, we know that the particles less than the speed of light and particles at the speed of light, they exist. Particles moving at speeds greater than the speed of light don't exist, because experimentally we have not seen it. It turns out that to understand conceptually, to build up a theoretical formalism in which such particles can be accommodated is much more challenging. They lead to sort of inconsistencies and so on. So normally what happens is that if you construct a theory, in general such particles turn out. You have to do something smart to do away with those particular particles, otherwise nobody will believe your particular theory. So theoretically there do exist particles which move greater than the speed of light. So the exact statement is you can't change their character. They have to, it's like a caste system. Once you are born with speed less than that of light, you cannot become a particle moving at the speed of light. Okay. Yeah.
Like light moves at the speed of light.
Huh? Say?
Light moves at the speed of light.
Huh.
Light, let's say, goes into water or something. So
That's a good point. So the vacuum word is very important. So, you are perfectly right that when therefore, when light moves in a medium, then because of the interaction with the medium, of course, as you said, the speed can
You're making something that moves the speed of light through your action
right.
move slower.
Yeah. So, no, but that is so remember this. So, there it's you understand that, right, you understand it, that light is interacting. So, what is happening with light is, so if you do the theory of electromagnetic interactions with matter, then you know that it's those interactions which are reducing the speed of light from whatever it is to something which is sort of less. But then people are asking these questions, can you make media more, can you be smart enough to make media to do what she wants, can you make it move faster than that of light, can you make the interact, no. So, there are people are trying to push the boundaries of what you can do with interaction of material with light, and it's a very what you call a very hot theoretical subject. So, for example, making invisibility cloaks and so on, right. I mean, all this really requires you to do understand very critically how light interacts with matter. So, it is a very important research area, and that is the reason, as I said, one should not say that it is proved once and for all that this is the case. There is a boundary where you can push, and finally, if you can find a small what you call reason to what you call go across that particular theorem, then you may find something, and that is exactly how physics proceeds, that the theory is based on a few assumptions, but if you can try to circumvent that assumption, then your theorem will no longer hold in that strong form, and maybe that is how you may be able to do something. But as of now, all people's attempts to look for a particle moving faster than that of light, it has not yielded something. But it does not mean that such a particle may not exist, will not exist, and if it exists, we have to really be very more creative to understand, go beyond our present understanding of what the theory is. Any other question? Yeah.
So is it a valid question to question the speed of light itself, why it is what it is? Is it an intrinsic property of light, or?
So, you see, so you would have sort of realized by now there are, every question is not sort of answerable. So, for example, why is G equal to so much? Why is E equal to so much? Right? Why is it that as you are asking this question, why is the speed of light the fundamental thing is nature? Really, there is no, I don't think there is a good answer to it. The best answer, as I said, is that okay, I began by allowing my speed of light to be different, and I did all kinds of very sensitive experiments to look for variation from that, and try what I may, I have not been able to do something, and therefore I look at it as an experimental fact. Now, there is a theoretical very loose argument which people sometimes give, saying that suppose we apply the principle of relativity to light itself, to electromagnetism. See, all interaction should follow the principle of relativity. So, electromagnetism should also respect the principle of special relativity. Now, where do you get the speed of electromagnetic light coming from? So, you take Maxwell's equations, and from Maxwell's equations we get the speed of light, because we get a wave equation, and in that wave equation for electromagnetic waves we get the speed of light, and then we say light is an electromagnetic wave, and therefore. So, then some people argue that this particular speed which comes from Maxwell's equation, because it is appearing as a part of the fundamental theory, this speed of light is some fundamental property of the electromagnetic interaction, and therefore it has to be the same. But okay, if you are happy with that, that is a better argument. But I would say that at the end of the day, the point is that it's an experimental fact, and one should never forget that we are physicists and not mathematicians. As a mathematician, you can imagine other things, but as a physicist, we are bound by experiments which we do. Okay, you had a question, yeah.
So you said that the Lorentz transformations are used for relativity. What is it about the Lorentz transformation that it scores over Kelvinian transformation?
Yeah. So, the way you understand it is that when you are doing the Galilean transformation, right, at that particular point we assumed that time was absolute. Right. Now, when you are trying to derive the Lorentz transformations from the beginning, you built in from the beginning this fact that this whatever transformations you come up with have to give the same speed of light in both the frames. So, you build in into the derivation the fact that the speed of light has to be the same, even though I am looking at a primed frame and an unprimed frame. If I look at the propagation of light in both these frames, they really have to have the same speed c. It is not c in one frame and c prime in another frame. Because you are building that in from the beginning, and when you go through the derivation, you get a set of transformations which we call the Lorentz transformations. And then when you look at that Lorentz transformations and then go to the limit when your frames move with smaller velocity, then that transforms into the Galilean transformations. So, you say that, well, I have a transformation which is valid for all possible velocities close to the speed of light, not only for small velocities, but also for velocities close to the speed of light. But if I take the limit of this for small velocities, then it reduces to the Galilean transformations. So, then you say, now I understand why it happens. Ordinary life never used velocity speed to the speed of light. I cannot do an experiment moving at the speed of light. I can only do velocities at small. So, my experience will only give me transformations which are like Galilean transformations. But today you can do experiments in the accelerator labs. You can take an electron and make it move at close to the speed of light. Now, you do the dynamics of it, and then you will find that the dynamics is not the dynamics of Newton, but the dynamics of Einstein. So, today you can actually do the experiment, and if you try to use Newton's laws of motion to predict how an electron will move in an accelerator, your answer will be completely wrong. But the moment you use Einstein's generalization of that, then your prediction is exactly right. So, because of all this, we believe that Einstein's theory is a better theory, as I explained. Newton's theory is good for small velocities, but Einstein's theory is good for all velocities, including velocities close to the speed of light.
There is nonlinearity subsumed in Lorentzian transformation.
Not for the nonlinearity, because the Lorentz transformation is still linear.
Just a matter of measurement. The speed of light is different. I mean, it reduces in media, and as we measure it in, let's say, vacuum. But how absolute is that vacuum? I mean, what if it's so? Maybe the actual speed of light may be a little higher than that, and what we take as granted is.
Yeah. So that is the whole point, right? I mean, so that is the reason physics really becomes a fight against every decimal place. For example, today we can have vacua of 10 raised to minus 13. So, we can do the experiment in that particular value. Tomorrow, we make it 10 raised to 80. So, that is the whole point. The challenge is that over the last, let us say, 100 years, our experimental techniques have become more and more sophisticated, and still all these laws which we have discovered are valid. But we really want to push it. See, we are not, when it works, we are not interested. We are interested in that particular regime where it breaks, because only when it breaks, see, normally here we get very upset in ordinary life if somebody breaks something which we say. But as scientists, we are always looking for something to break down, because it's only when something breaks down, it tells us that there is some understanding beyond what we have understood. We are going on a smooth curve, but that is not something, something new cannot be discovered. So, it's only when something breaks, then it tells us that, well, you have not taken into account everything. Maybe some new phenomena is there in that particular case. Some new, as you said, as you explained, maybe there is some nonlinear. We have been assuming linearity all the time. Maybe there is some nonlinear effect which has to be taken into account. Or, as you rightly said, in the vacuum, there are some newer interactions which are possible. So, then you really try to confront your experimental observation, and of course, normally many times the experiment, when you are doing a very sensitive experiment, you have to be very careful that you are not making an experimental mistake. So, that is the reason whenever you do all these experiments, it becomes a big challenge to first make sure that it is not because of some trivial thing which is going wrong with the experiment. So, you would repeat the experiment many times by different groups, by different ways, and then if you see it consistently, then you say, something has to be understood, our theory has to be extended, and something new has to be, and that's how a new theory comes into being.
So actually, it is given in the Feynman's QED book that light appears to slow down, but it doesn't. It is explained with some zigzag paths or something like that.
So you tell us, no.
So according to what he said is when light actually slows down.
So it slows down, right? You are saying it's not slowing down.
It appears to be slows down. He says that in that particular book.
No, but in what context he's saying?
Conclusions from that statement will be wrong.
No, but it slows down, right? I mean, you can measure the speed in a vacuum and it slows down. So why are you objecting to that empirical statement? No, but no, to me it slows down, right? I mean, irrespective. I mean, I don't know in what context Feynman is saying that it appears to slow down, but I am saying that he is talking about the measurement of the speed of light in a medium, and there it slows down. So I don't see why you should quibble and say it appears to slow down when it really slows down. Okay, no. So you understand something which I don't understand. So.
Maybe what he means is it has the same speed, but maybe it bounces around a little bit. So
It's zigzag. He explains
overall-
Yeah, but that is.
using the medium. He explains with different. He explains.
But that is. But the whole point is precisely that, right? The moment you have in a media, you have interaction, but that path itself is an imaginary thing. You have to understand that Feynman's path, you are assuming that the path integral means that path is more important rather than the material thing. I think that is wrong. That is just a description. I mean, there are paths, and in that particular space of paths, you try to calculate the probabilities and so on. You are giving, real existence to a mathematical theory which explains all these things. You have to, you have to distinguish between a calculational tool and a physical fact, right? So, according to me, you are referring to the calculational way. I mean, if the light is going through a medium, then how am I going to calculate that, right? And that is consistent with what he's sort of saying. That there are scatterers and so on, and therefore you have to take into account that. But that is different. But if you are an experimenter, I mean, you are not interested in all the paths which contribute to that. You are just interested in saying, if I send the light from here to this particular point, how much time it will take, because I have probably put something there which will burn if I don't do something about it. So you don't care whether it scattered or whether it came something. I'm just saying that you have to understand, you have to distinguish between the level of reality of what you are. You somehow seem to be stuck to the mathematical description of it, right? We are talking about, in fact, I am trying to put the other viewpoint, that physics is not mathematics. Physics is all about discovering what the thing is, and then there is a theory by which we try to understand it in a very simple way. And one should not confuse the mathematical description with the fact. And somehow in every question which you ask, I find that confusion between the mathematics and the physics, and that's something which you have to work on. We can talk about it in a separate session. Any other questions? Otherwise we go to the next part. So we have traveled a lot. We have come to special relativity, and it's only now, right, after an hour, that we really come to the topic. And you can see why I really went on it, because there's no point in seeing what changes are there unless you know what was the older picture, right? So now we have gone through the whole paradigm, starting with Newton, starting with Galileo, then coming to Newton, then coming to Einstein's 1905 work. And we understand that if you were living in 1905, special relativity has been discovered, and then we have realized that Newton's absolute space and absolute time is not consistent with physics, and we have to look at the whole universe, the whole physics in terms of space-time, and that is where we are. So 1905, Einstein writes these great papers, 3 great papers, which basically gave special relativity, statistical mechanics, and quantum mechanics, and then you think that he will retire. But then 1907 to 1915, is the most heroic struggle in his life, as I will try to show. So, what we learned is that if you look at special relativity, Newtonian mechanics needs to be changed, because as we said, you cannot make things move. Dynamics really is not the same. F equal to ma, but what you call as m really has to include special relativistic corrections and so on. And therefore, as we learned, if you are moving at speeds close to the speed of light, as we do in accelerators and so on, Newtonian mechanics will give completely wrong answers, and we have to use special relativity. Right? That is what Einstein really proved. He also proved, energy, E equal to mc square, right? So which basically tells you that rest energy is nothing else but rest mass is just one form of energy. Then electromagnetism, Maxwell's equations was completely known, but just because special relativity came, unlike Newtonian mechanics, nothing needed to be changed about electromagnetism. The laws of electromagnetism as written by Maxwell exactly remained the same, even though our picture of space time changed. Absolute space has been thrown away, absolute time has been thrown away, but Maxwell's equations require no change. Then obviously the question which you would ask is, at that particular time the two interactions which people knew were electromagnetism and gravity, because gravity was something associated with Newton. So the question obviously you would ask is, what about Newtonian gravitation? For more than 200 years it has been a successful theory. One understands the solar system. So can we take, or can we believe exactly everything which Newtonian gravitation tells us? Because we believe that special relativity is also an important part of nature. And therefore, to really do it a little more pedagogically, I will just look at the force of electromagnetism and the force of gravitation and try to see what are the things which are similar and what are the things which are different. So let us just go through these tables. So for example, if you look at electromagnetism, if you have two charges, the force between them is given by Coulomb's law, and on the other hand we have Newton's law of universal gravitation. This is an inverse square law, there is also an inverse square law. Anything which has a charge will have an electric force. Similarly, anything which has mass, as we said, it is a universal law, so it will also have a gravitational force. Now comes the first difference. There are two kinds of charges. Experiments show that there is something called a positive charge and a negative charge, but in gravity there is only one kind of mass. We do not talk about positive masses and negative masses. Then, because of the fact that there are positive and negative charges, here the forces are both attractive and repulsive, whereas it is only attractive here. Now again a strange thing, when do the charges repel? When they are like charges. Here obviously there is only like charges, right, because everything is only one kind, but they are attracting. So you can see that though at some superficial level some things are similar, when you start looking into the details, there seems to be a big difference between the electric case and the gravity case. More importantly, when you compare the strengths, compare the electric force between two charges and compare the gravitational force between those same charges, you know that there is a factor of 10 raised to 39 between these two forces. That is, compare the two forces between two charges and compare it to the gravitational force between them. So you can see that it is a very, very weak force, but there is only one kind of those particular forces. And because there are two kinds of forces, I can always screen it. I can take a negative charge, put a positive charge against it, and then if I go outside it, it is like a total zero charge situation. So I can screen the effect of the negative charge by putting a positive charge. Here you cannot screen, because there is only one kind of charge, so there is no question of screening it. So in some sense, this seems to be something which, if it is once there, it is there, you cannot hide it away. That is one important difference compared to whatever is happening here. Again, when you look at the force picture, we say that it is an instantaneous action at a distance. We have 1 by r square, and the moment if we put two charges, they will have electric force. The moment you put two masses, they will have gravitational force. Now, let us look at the next part. If I have a charge, this is something which when you learnt your electromagnetic course you would have learned. I have a charge, this charge, suppose you ask for its field, you can use the Coulomb force and then you will find an electric field will be associated with that. Take the same charge and now move it. Now, in addition to having charge, because it is a moving charge, it is a current. So, associated with this current there will be a magnetic field. So, if I have a static charge, it has only electric field. If I have a moving charge, it has both electric and magnetic fields. Whereas, if you look at Newton's mass, the gravitational field is basically determined by mass itself. It is not determined by whether this mass is at rest or whether it is moving. So, in this particular case, you will find that whether you have a static mass or a moving mass, they will produce the same gravitational field. So, there is a difference. In this particular case, there is something like a dynamical electromagnetic field. Here we have only a static electromagnetic field. So, there is again a big difference between them. These are given by Maxwell's equations. Here, as you know, they are given by Newton's equations. The equation of motion here, as you know, are given by Lorentz equation of motion. Here, of course, you have the Newtonian equation of motion. The important reason why Maxwell's equations did not change when special relativity came is because what we say is the equations of electromagnetism are invariant under special relativity. That means, if you take Maxwell's equations and go to a uniformly moving frame, the equations keep the same form. That is the reason when special relativity came, Maxwell's equations did not have to be changed. But if you take Newton's equations of motion and make a Lorentz transformation, the equations form changes. So, obviously, that is the reason Newtonian mechanics had to be changed and you had to come up with relativistic mechanics. So, this is the important point, that because this is invariant as a special relativity, it is very clear that Newton's theory is not consistent with the special theory of relativity. So, 1907, Einstein realizes that even though Newton's theory is a successful theory of gravity, it has a problem if you confront it with special relativity. And he believed that special relativity is a law of nature. Special relativity is something which has to be true. So, any law of nature has to be consistent with special theory of relativity. So, the next question, and then of course last point, that as I said, that sources are charges and currents, and here as I said, according to Newton, it is only the rest mass which is the source of this particular theory. Now, when you look more broadly between special relativity and gravitation, special relativity implies a maximum speed for interactions, but the moment you talk about instantaneous interactions, the speed of interactions is infinite, right. If I have two charges, how long does it take for the gravitational force to be there? There is no time in that particular equation. The moment charges are there, the interaction is there. So, it is like saying that the moment you have instantaneous interaction, it is like moving with infinite speed. But according to special relativity, nothing can move at infinite speed. So, if you take Newton's laws of gravity, it cannot be consistent with the special theory of relativity, because that can only be true if the speed of propagation of gravity is infinite. Then again I told you the same thing. The source for Newtonian gravity is only the rest mass, but I told you that in special relativity energy and mass are equivalent. There is no difference between energy and mass. So, according to special relativity, mass and energy are equivalent. So, if you believe in special relativity, the fact that only rest mass will have a gravitational field and kinetic energy will not have a gravitational field is not very satisfactory. So, only having static gravitational field and not having dynamic gravitational field is not a good thing once you believe in special relativity. Now, these are all theoretical things, but experiment, as I always keep telling you, is one very important guideline for Einstein. And what was the experiment in this particular case? Now, this experiment goes back again to Galileo. You must have heard the story about the feather and coin experiment, where he is supposed to have gone up the Pisa Tower and dropped two things and showed that they fall at the same speed. Now, this is something which is an experimental fact, that bodies fall with the same acceleration if the gravitational field is uniform, independent of composition. Now, it turns out that this is something which is today experimentally tested to a very large accuracy. For example, one can calculate the rate at which the moon and the earth fall towards the sun, and to an accuracy of about 10 raised to minus 13, these two objects are falling at the same acceleration. The composition of the earth and the composition of the moon is very different. So, obviously, it means that different bodies made of different composition move at the same acceleration. Now, this is something which Newton was also aware of, and if you do a simple calculation for yourself, you can do this. I will explain what is the calculation to do after the next slide. Newton himself realized that this was something which was there, and Newton is supposed to have done experiments to verify that this is such true. He made pendulums of different material, and as I will explain to you, by using this our ordinary pendulums, one can try to show that this particular fact is really true. So, this particular statement is an experimental fact. So, this is the analog of the experimental fact that the speed of light is the same in all initial frames. This was a statement which Galileo knew, Newton knew, but Newton's theory of gravity has no fundamental explanation of this. Einstein was struck by this remarkable feature that of gravity, which up till now was just treated as a mere coincidence. This essentially is the hallmark of Einstein, to really look at various things and then identifying that there is something in this particular fact which you have to understand, and only when you understand that you will have a better understanding of nature. The first thing, in the case of special relativity, it was the speed of light. If you remember popular books, he is supposed to have asked, if I sit on a frame which is moving at the speed of light, what will be the speed of light? So, it is a question which he asked, and for 7 years he juggled with that particular question, and finally, when he had the special theory of relativity, this question was answered. In the case of gravity, this fact stuck him, and of all the other people who tried to make a better theory of gravity, Einstein was one person who basically said that this is a remarkable statement about nature. Why is it that a ball of mercury and a ball of gold, a ball of platinum in the same gravitational field, they should fall with the same acceleration? So, he was struck by this, whereas most of the other people, even great people like Newton and Galileo, they knew this, but they had to leave it as a simple coincidence. It is something which is an accident, it has no fundamental implication. Now, why is this fundamental? This is what we will explain in the next few slides, and this is exactly what I want to say, that one makes the progress not just by coming and with the right answer, but before that you have to ask the right question. So, asking the right question is the key to making progress in science, and the right question which Einstein, as I explained, is this, and in his writings he is supposed to have said that this thought which he had was the happiest thought of his life, and this thought is what led to the general theory of relativity. So, this is called, just as this is given a name called the equivalence principle. Why it is called the equivalence principle, I will explain later, but let us just see what he is saying. Then occurred to me the happiest thought of my life in the following form: the gravitational field has only relative existence, because for an observer falling freely from the roof of a house, there exists, at least in his immediate surroundings, no gravitational field. If the observer drops some bodies, these remain at rest relative to him in a state of rest or uniform motion, independent of their chemical or physical nature, ignoring of course air resistance. The observer has the right to interpret his state as at rest. Now, what he is describing here is nothing but the problem which you do in your 12th standard, where you have a spring balance attached to a lift, and then you are asked this question, that if this lift is accelerated upwards, what is the reading of the spring balance? If the lift is accelerated downwards, what is the reading of the spring balance? And if some of your friends cut the cable, then what is the reading of the spring balance? This is a problem which we do from 8th standard, 11th, 12th, etc. But this has something, is supposed to be described by Einstein as the happiest thought in his life, and it is this thought which, as I will show, really was the beginnings of his general theory of relativity. Now, so this is why I call it Einstein's lodestone. It is something which showed him the direction. Basically because, why do objects fall at the same rate? Why is there universality of free fall? It is basically because there is an amazing coincidence between two totally unrelated concepts. The concept of mass, which is called inertial mass, and the concept of mass, which I will call gravitational mass. Now, what is the difference between them? In Newton's second law, there is mass which appears, right, F equal to ma. What is that mass doing? It is measuring the inertia of the body, right. So, therefore, that is what we will call the inertial mass. There is another mass which appears in Newton's theory of gravitation. It is something which tells you how much will be the force of gravity. It is like the electric charge. Electric charge tells you how much will be the force of electricity, electric field. So, obviously, one is a measure of inertia, one is a measure of how much gravitational force it will create, and in principle they are not really two things which need to be the same. So, there are two notions of mass which appear, and they will be equal, because when will they be equal? You do experiments, and when you do these experiments, what will appear in these experiments is the ratio of these two objects. In fact, I do not have to do this exercise on the board. You yourself would have done this exercise when you decided to do the problem of a charge moving in an electric field. Do you remember? If you write the equation of motion for a charge in an electric field, you will write F equal to ma, but what is force? Charge into electric field. So, you would write that, and if you therefore measure what the acceleration is, it will always depend on the ratio of charge to mass. It will depend on q by m. Now, q in the case of gravity is gravitational mass, m in the case of gravity is inertial mass, and therefore, the acceleration will be the same only if the ratio of inertial mass to gravitational mass for all bodies is a universal constant. So, the fact that all bodies fall with uniform acceleration really is a statement that the ratio of inertial mass to the gravitational mass is independent of composition. And as I said, Newton was aware of this, but there is no explanation of it. Einstein was convinced that this coincidence was a vital clue and the most fundamental fact about gravitation, and only if your theory of gravity built in this from the beginning, you could get the correct theory of gravity. So, this is exactly why he called this the happiest thought of his life, because according to him, it is this particular fact which had to be built in any theory of gravity which you would come up with. And the important point, as I told you, is it took him 7 years to come to the final theory of gravity. There were many things which he gave up, there were many things which we made mistakes on, But this physical fact he never gave up. He held on to this conviction through the 8 years it took him to arrive at the field equations of gravitation, and it is seen as the first step in his formulation of the general theory of relativity, and this is called the equivalence principle. So, as I said, the important thing about Einstein, whenever you look at his theories, it seems to have so much mathematics that you believe that Einstein was a mathematician. But what you will really see is that at the core of it there is a physical insight, and it is that physical insight which makes Einstein different from all the other people who did very similar things like what Einstein did. For example, Poincaré is supposed to have done very similar things like Einstein, but the insight which Einstein had in creating special theory of relativity, or the insight which Einstein had in creating the general theory of relativity, is completely unique, basically because he had this uncanny nature of asking the right question and being able to identify what was the core physical fact which had to be not compromised in the theory which you sort of build in. And that for the theory of gravity. So, remember, he is trying to build a theory of gravity. Suddenly, why is he going off in a tangent, right? We would have thought that he will just take Newton's theory of gravity like other people did and try to make it consistent with the special theory of relativity by just tinkering here and there. He did not do that. He said, okay, let me try to ask what is fundamental about gravity and then try to build my theory. He did not do the mathematics first. He looked at the physics first and then latched on to that physics till the end without giving it up. And he had this conviction that his physical insight was much better than everybody else's. Other people did not believe in him, but he believed in whatever was his perception. So, now having told you, how one comes to the why this is a fundamental fact, I now have to explain to you what is meant by this equivalence principle. So, this equivalence principle is a statement that if you have a gravitational field, locally you can eliminate it by free fall. What is meant by free fall? Just go to the lift and cut the cable. That means just fall freely in the gravitational field. Similarly, you can mimic a gravitational field by acceleration, and by a mechanical experiment, as we know, you really cannot distinguish between the two. So, this is basically an important point. And then if you want to generalize this, you basically say that if you do experiments in a small lab over small times, then you cannot distinguish between the results of experiments which are done in an initial frame or whether you are in a frame which is falling freely in a gravitational field. So, his equivalence principle is the idea. So, remember, in mechanics we know, actually we can prove it, but his equivalence principle, as he always did, basically is this insight that you cannot do things only for mechanics, you really have to apply it to all of physics. So, his equivalence principle is the idea that do whatever experiment you like in physics, you cannot distinguish between uniform acceleration or a uniform gravitational field. So, suddenly you are sort of realizing that in trying to go from special relativity to understand the gravitational field, he is coming to the conclusion that in addition to uniform motion, you really have to look at motion which are accelerated, and that is the reason we call this theory the general theory of relativity, because if you want to describe the gravitational field, we have to allow for a more general class of observers, who are not just moving uniformly, but who are accelerated. Now, it is very easy to understand it by this experiment which is usually called as the Einstein's elevator. So, let us look at the various situations which are there. Situation A, this elevator is sitting on the earth and I have a spring balance from which a body is hanging. Situation B, this lift is not on the earth, but in free space. situation C, this lift is in free space, but it is accelerated in this direction by exactly the value g, and this which is on the earth, but freely falling. So, the equivalence principle is the statement that a lift stationary on the earth, so there is a gravitational field. If you do an experiment here, that means for example, here I am hanging this spring balance. Now, I have gone to free space where there is no gravitational field. Now, I take this lift and accelerate it in a direction which is opposite to the direction of g. Then obviously, in this particular situation, the spring balance would still be extended. So, by looking at this experiment here, I cannot say, I can't close my eyes and then say whether I am in this particular situation or I am in this particular situation. Similarly, in this particular case, I have a situation where something is in free space, there is no gravitational field. Here I am on the earth where there is a gravitational field, but then I cut my cable so that in the gravitational field it is falling uniformly. So, again it is like you are in free space. Now, the important point is when it is a mechanical experiment, it is very easy to see. What Einstein said is, if you did an experiment in electromagnetism or in nuclear physics or whatever, you cannot distinguish between what will happen here and what will happen here. So, this is the statement of equivalence principle. Now, to make the calculation simple, I said that I am assuming a uniform gravitational field, which is what we normally do, that near the surface of the earth g equal to 980 blah blah blah, right. We know that it is not constant, but we know that over a small region it can be considered to be constant. Now, in an actual gravitational field, it is not going to be uniform as we were discussing, right. It is going to change from point to point. So, then what can you say? Then what you can say is, go in a very small region around that particular point. In a small enough region, you can always assume the field is uniform, and therefore, your equivalence principle should hold. So, what Einstein said is, whatever be the nature of the gravitational field, whether it is non-uniform in space, non-uniform in time, it does not matter. Over a small region of space time, you can always go to a accelerated frame and transform away your gravitational field. Now, if you have transformed away your gravitational field, you are in a situation which is exactly like the situation of special relativity. So, whatever are your laws of special relativity, they have to be holding. So, you have finding a way to predict what will be the laws of physics in the presence of a gravitational field by going to a convenient frame, and this is exactly how he proceeded to construct his theory of general relativity and his theory of gravitation. So, you can see the experimental insight is that all bodies fall uniformly. From that, he is generalizing to understanding something about the nature of the inertial mass and the gravitational mass, generalizing it to all of physics, and then coming up with a principle using which he will try to come to his field equations. So, this essentially is the third part, where his physical insight is what I have explained, that this is the equivalence principle. So, 1907 he basically has come into this particular thing, he has understood this and has realized that whatever I do from now on, the principle of equivalence has to be built in or has to play a fundamental role in my theory of gravity. The next 8 years, right, there is again 2 more phases here. It will get to be a little technical in the last part, but again as I said, it is not to learn everything you have to go through a full course, but there is no difficulty at all in qualitatively understanding what is the fourth part. But before going to the fourth part, now let us just come to the third. In this third part, if you have any questions, let us take them. Yeah.
So gravity does take time to propagate.
Yes. So, essentially therefore, finally after we get the field equations, then from that when you ask, then we will come to that particular conclusion. So, once you set up Einstein's theory of gravity, exactly like it happens in the case of electromagnetism, gravity also has a finite speed of propagation, and therefore it becomes consistent with the special theory of relativity. Yeah.
So Einstein, he just made all of his conclusions based on experiments he did not conduct.
Well, the whole point is the experiment which were conducted, as I said, about bodies falling. So the what was not conducted is this generalization to physics, both in the case of special relativity and in the case of general relativity, when he said my relativity principle applies to all of physics and not just to mechanics. In mechanics you can do experiments and say, okay, I can do this, but his basic so that is where, as I said, some analytical insight into the structure of the theory becomes important, and the argument which I gave you, that whatever we say, it does not make sense if there is a fundamental principle that it applies to only one part of physics. It applies only to mechanics but does not apply to electromagnetism, because this difference of mechanism, mechanics, electromagnetism is something which is our mind creates so that we can understand nature in a simplified way. We try to break up nature into smaller sections because it's so complex. If we try to do everything at the same time, we can never conclude. So we try to break up nature into small parts, and then we try to understand experiments, try to understand the laws there, and so on. But at the end of the day, we have to realize that we are looking at phenomena, and in phenomena everything comes together, and therefore it is very artificial to assume that a broad principle applies to only one thing. So this was the insight which Einstein had, saying that, well, either it applies to everything or it applies to nothing, and he believed that, and the whole argument is that you believe it, come up with a theory. So you have a limited experiment. From the limited experiment you have a broader physical idea. After the broader physical idea, you make a prediction of a better theory. From the better theory you make an experimental prediction, then you verify that experimental prediction, and that experimental prediction therefore indirectly verifies the theoretical jump which you made, not word to word but qualitatively, and you keep on doing this iteratively.
So the way he said electromagnetism isn't going to change. Did he say that?
He didn't say it. You find it doesn't change.
Yeah. So did he conclude that from the fact that the speed of light is same in all?
No, you have the equations, and then you have, so there's you don't have to, it's a simple analytical calculation. Once you have Maxwell's equations, once you have Lorentz transformations, it's just algebra to verify that they have to be the same. Any other question?
Can we take a small break?
Huh?
Can we take a small break before the concluding section?
Yeah, 10 minutes.
Yeah.
In the last part. So as I said, this would be a technical part, so bear with me. So as I said, now Einstein's insight is that to understand anything about gravity, you don't have to go to do the gravitational problem. Actually go and try to see what happens in an accelerated frame, and then argue that because of the equivalence principle, in the gravitational field also a similar thing must happen. So he said, now let us look at what happens to a light ray if you are looking at it in an accelerated frame of reference. Remember that if you are moving in a uniform frame of reference, then light will appear to move in a straight line. But if you have an accelerated frame, you can do the simple problem for yourself. Take a lift which is accelerated, send light from one end to another end, and then just see what happens. How does the path look like if the lift is accelerated? Essentially, you will see that because of the fact that by the time the light ray goes from one end to the other, the lift would have moved half g80 square, and therefore, if you really look at what the path is, the path obviously would be curved. So basically, if you look at this particular problem, how light travels in a how does the light look like in an accelerated frame? Because the path is curved, if you believe equivalence principle, it means that if you have a light propagating in a gravitational field, then it should not path in a straight line, but actually have move in a curved path. And in 1911, he basically realized that it can be tested by experiments. So, he said that if there is starlight which is passing close to the sun, and if I look at the situation during an eclipse, remember you can't look at the light when there is ordinary time because the sun is very bright, but if you are in a situation where you can compare the star image when there is an eclipse and when there is no eclipse, you should be able to actually verify whether in the path of a gravitating object light bends or not. So, in 1911, even before his theory, just based on this particular argument, he had predicted this, and an experiment was also planned in 1914, but World War I happened and this experiment was aborted. The people were supposed to do this experiment in Russia, etc., and only in 1919 this experiment was really confirmed by Arthur Eddington, and this is another story. It is this particular experiment which made Einstein an icon of physics all over the world. But you can see that even without going to the full theory, he has really been able to do something and predict something which could be tested by experiment. The other thing he sort of realized is that if you have an accelerated observer, if you say for example he is moving in a curved path, then essentially you are saying that the speed of light as measured by this accelerated observer is no longer a constant, but it is it's not a constant anymore. So, again he goes to the equivalence principle argument and says that if there is a gravitational field, then the speed of light will be affected because of the presence of gravity. So, the whole argument after this is what somebody, historian of science, called the tinkering phase. He basically assumed that equivalence principle is fundamental and then did small things to try to understand what will be the nature of the modifications which you have to do, so that the effect of gravity on light is automatically built into this particular theory. Now, this can be seen today in another way. For example, if you think of a tower, and if I have light passing going from below to the top, in our present way of thinking about it, even though light has is a photon made up of zero mass, obviously it has some energy, and therefore there will be some potential energy associated with it. So, if you send if the light has to go from the bottom of the tower to the top of the tower, in some sense it has to do some work against the gravitational field. So, obviously if light has some frequency at the bottom of the tower, at the top of the tower it will be different. So, this is essentially what is called as the gravitational redshift, that in a gravitational field light, and if you think of the fact that it is a redshift, if you make clocks by using this, obviously it means that the clocks run at different rates in the gravitational field, and that is exactly what he is sort of saying here. So, there are different ways of seeing these things, but the important point is exploiting the fact that whatever you can do with acceleration, that same thing has to happen in a real gravitational field. Then is a very interesting thing about, somebody asked me about geometry. This is an interesting point which he made. So, as I said, if you are looking at an elevator, the elevator is uniformly accelerating. Then he said, what about a uniformly rotating frame of reference, because that is also an accelerated frame. Is that equivalent to a gravitational field, and does it give us any insight which is different? Now, some historian of general relativity basically said that this is what he called the missing link in the history of general theory of relativity, for the following reason. You have a rod, you have a disk which is sort of rotating, and on this disk you do the following experiment. You know that special relativity is correct. So, there is something called Lorentz contraction. So, if you have a rod, a disk which is rotating, and I try to measure the length of a rod once by keeping it along the circumference where there is a velocity, and once along the radius along which there is no velocity, then obviously the rods along the circumference will have a contraction, the rods along the radius will not have a contraction. So, if you are a mathematician and want to calculate the value of pi, you will take the ratio of the circumference to the diameter, but if you are an observer who is on that particular frame, his answer for pi would be different. because if you are ordinarily sitting on a non-rotating disk, then you will get pi, but here because of the length contraction. So this particular experiment, it goes on in his mind, and then he immediately knows something about non-Euclidean geometry, and then he basically sort of says that, well, therefore it gives him an idea that when you are talking about gravitational fields and you are talking about space time, maybe one has to be careful that it will not be the same space time of Minkowski, but a non-Euclidean space time as hinted by this particular example. Now, why did I call it the missing link? Because if you really look at the writings of Einstein and so on, it is never explicit like this, but you do find many letters which he writes to many of his colleagues and so on, where he discusses this. Later on, when he discusses how he discovered general theory of relativity, again he goes back to this particular point. Now, there are subtleties when you use this particular argument, so I will not push this too much, because as somebody who's known in who will know in mathematics, you would know that even though in this particular case you are probably using coordinates which are when you really look at the actual geometry, whether it really changes, then you have to do something else. You have to really calculate what is called as the Riemann tensor, and then it really turns out that this argument is really not as foolproof as we would like it to be. So the important point is whether this is a coordinate effect or whether it is really a physical effect is something which this example really doesn't give. But what the historians basically feel is that just as we talk about the acceleration, linear acceleration example, the elevator example, Einstein's general feeling that the geometry of the non-Euclidean geometry is important to describe the gravitational field really came from his understanding of this particular example. There is another example, again when you read popular books you would also sort of realize that he talked about what is called as the rotating bucket experiment. So again this has some connection with some ideas of Mach, etc. They tend to be a little confusing, so I won't sort of really go through the full history of all that thing. But the important point is, as you can see, he has an idea and he is tinkering with various things so that he can get an idea of how to go beyond special relativity. So what he does then is the following. He basically knows that if you want to describe two-dimensional non-Euclidean geometry, you can you use curvilinear coordinates, and therefore when you have a static gravitational field and you want to describe mechanics there, you basically try to write a Lagrangian or try to do a variational principle in that particular case. And he basically therefore, and then in that example which I told you, he understands that probably there is a notion of a non-flat space-time which is sort of required. So it looks like that he puts these things together and then realizes that if you really want to describe the gravitational field, the mathematical object in terms of which you should think about the gravitational field is something which I will explain, which the mathematicians call metric tensor. Now what is the metric tensor? It is very easy to understand. See, for example, if I have this space here, if I take 2 points, what is characteristic about these 2 points is that if I have these 2 points, I can tell you what is the distance of these 2 points by writing the distance formula, right. So what is the distance formula if I use Cartesian coordinates? You will say the distance is x square plus y square plus z square. If the 2 points are very close to each other, you will say if the distance is dx, I can say it is dx square plus dy square plus dz square. So essentially, if I have this flat space, I have this form which is called the line or the distance between the 2 points, and the coefficients of this x square, y square, z square, because this is a Cartesian coordinate and this is a flat space, is just 1, 1, 1. The moment we went to space time, we talked about Minkowski space time, and there not only we have to talk about space, we have to talk about time also. And there if we write down what is the separation between 2 events, not separation between 2 physical points, then again we say it is given by c square dt square minus dx square minus dy square minus dz square. So, what is it giving you? It is giving you the distance between two events. But if you think of this as a geometry, again this minus 1, 1, minus 1, minus 1, minus 1 in some sense describes this Minkowski space-time for me. It is these coefficients which are basically called the metric tensor. So, if you have in general a 4-dimensional space-time, you can ask how many independent terms are there, right. It will have dx square, dy square, dz square, all the cross terms, etc., the dt square. So, if you put all the coefficients and ask how many independent terms are there, it is very easy to do the counting because you are in 4 dimensions and you are talking about a symmetric object. So, the answer turns out to be just 10. So, you can see that if you want to describe the gravitational field in Newtonian physics, you just have a potential, just one function to describe the gravitational field. Now, Einstein slowly is going away from there. He first talked about the equivalence principle. From the equivalence principle, he has come to non-Euclidean geometry, and from the non-Euclidean geometry, now he is trying to guess what will be the mathematical object which will describe the gravitational field. And then he comes to the conclusion that the metric tensor is a good object because the metric tensor will describe the geometry of this particular object and also the coordinates which you are sort of using. So, this is the next insight, and this insight which basically he had, saying that this metric tensor represents two things. It represents the gravitational field if there is matter. It represents the space-time structure also, because in the Minkowski case, the moment you had the Minkowski space-time, you can draw, you could you know the light cones, and that basically gives you what the space-time structure is. But then he is basically saying that when there is a gravitational field, then the metric tensor also represents the gravitational field. So, as you can see, it's getting a little technical, and then the whole exercise is, once he realizes what is the mathematics to be used, then the exercise which he had to do, which was very complicated, is that you are working in a non-Euclidean space. So, you have to understand that how is matter to be described when you are talking about matter in a non-Euclidean space, and then the last and the hard thing is what is the correct equation which the gravitational field will obey, so that it generalizes Newton's theory of gravity. So, as you can see, after he got the physical insight, the whole thing becomes a little more technical, and at some particular point in after 1912, he sort of realizes that this is what he requires, but he does not have the tools to really do it, and he really has to discuss with his mathematical